Today I'm going to talk about the tsunamis, just the basics of tsunamis, and also on how to generate the warnings on tsunamis. If you all remember, we experienced the devastating tsunami in 2004, precisely on 26th December, which killed more than 2.5 lakh people in the Indian Ocean region. In India also, we lost more than 10,000 lives, and that gave us the rude shock that the tsunamis can create devastations, unimaginable devastation in our country as well. Till that time, we didn't had the capability to issue the tsunami warnings. Soon after that, Government of India decided to establish the Tsunami Early Warning Center, and Ministry of Earth Sciences was given the charge to establish a center, and Ministry of Earth Sciences asked INCOIS, or International Center for Ocean Information Services, to establish the Tsunami Early Warning Center for India. Of course, the performance of the center was great. It was as per the international standards, even much above the international standards existed at that time. Hence, the UNESCO, the UN agency called UNESCO, which is coordinating the tsunami early warning services in the oceans all over the globe, designated this Tsunami Early Warning Center as the responsible center to provide tsunami early warning services for all the countries on the Indian Ocean rim. So we have developed that expertise. So I just would like to share some of our experience with you. Basically, I just want to tell you about the basics of tsunamis. What are tsunamis and what causes them? How we can generate the early warnings. So with this introduction, let me go to my present talk, and I will try to be very non-technical so that all of you can um, follow this talk. So the title of my talk is Tsunami Basics and Warning System. We are very familiar with tropical cyclones because in our country we get tropical cyclones almost every year, and the major ones, the recent ones are Feline that hit Odisha coast, and Hudhud that hit Visakhapatnam in Andhra Pradesh. And in 1990 there was a great cyclone which hit Odisha coast, and nearly 10,000 people lost their lives. So we get cyclones frequently, almost every year, either during monsoon or and most devastating cyclones are post monsoon during October November period. And now today we know how to detect the cyclones when they form over the oceans and issue the warnings. And along with the cyclone, there are storm surges, or cyclone piles up a lot of water on the coast, and that is causing most of the destruction, inundation of the villages, flooding of the villages, devastation of the houses, and killing the people who are staying there. Similar effect is caused by tsunami as well. Tsunami also comes and hits the coast and floods the villages and takes away the houses, boats, people, whatever is on its way, it takes out in the sea. But there is a major difference between these two. Today, we can detect the cyclone much before, at least a few days in advance, and issue the warnings, exact location where the cyclone is going to have the landfall. And we can also find out for that particular cyclone what would be the height of the storm surge, how much flooding it is going to cause, and we can issue the early warnings and inform the governments that these are the areas you are going to have a storm surge. So please evacuate all these people from this coast. And we can give the government more than 24 hours time to act upon. But the difference with the tsunami is that we still do not have any technology, or the science has not developed to detect the tsunamis in advance before their occurrence. So tsunamis we can detect, or we can warn only after its occurrence. So after its occurrence, we are mostly left out with very few minutes to few hours. For example, if I take 2004 tsunami, which was caused by a large earthquake of northern Sumatra. Sumatra is an island in Indonesia. It is south of our Andaman Nicobar group of islands, and it is thousands of kilometers away from the mainland India, our east coast, Tamil Nadu, and Andhra Pradesh or Odisha coast, but few hundred kilometers away from our Andaman Nicobar Islands. So that earthquake generated the tsunami, and the tsunami reached our Andaman Nicobar Islands within 20 minutes, because they are very close to that region. So tsunami wave could reach fast there first. And for our mainland areas, for example, Nagapattinam experienced devastation, including some pockets in Kerala. People are killed. So for those regions, we had a 2 to 3 hours time. For Kerala coast, 4 hours. So if we had a warning system at that time, we could have saved all those people from getting killed in the tsunami. So the time available with us is very short, not more than few hours, and for nearby areas only few minutes. So we should be very careful about the tsunamis, and the tsunamis do not occur very frequently. Of course, we know that after 2004, no tsunami has occurred in our region, and during our lifetime, we don't even remember any other tsunami. So tsunamis can occur anytime. It may not occur very frequently, but if it occurs, it is a devastating. It is very devastating. So that keeping these aspects in mind, let us look at what are tsunamis. So tsunamis are nothing but the large a system of ocean waves that are formed as a result of large scale displacement of seawater column, and they can travel long distances without losing the energy. So the tsunamis will occur if there is a large disturbance of the ocean water column. Normally, the entire water column is disturbed. If you have a large earthquake on the ocean bottom, then the entire water column gets disturbed, and it will generate a wave that is called tsunami. This word tsunami came from Japanese language. Japanese language, su means harbor and nami means wave. Because earlier when tsunamis are much more frequent in Japan than in other countries. There are reasons for that. I will come to that little later. So these tsunamis, when they occur in Japan, much before maybe a few hundred years ago, they used to see that whenever there is a tsunami, the whole harbor gets disturbed, and the ships jump up and down, and they hit each other because of their violent motion. Because the harbor, a large wave is generated in the harbor. So that is why they called it as harbor wave or tsunami. And we today we call this kind of waves as a tsunami. If you are out in the sea, in the deep ocean, if a tsunami passes, you are on a boat or a ship in the deep ocean, you will never even realize that a tsunami wave has passed you. Because in the deep ocean, the wave, the height of the tsunami wave is less than a meter. It is nothing more than a few tens of centimeters, maybe 30 centimeter, 40 centimeter. And you will never even realize if ships are out at sea during a tsunami, they are very safe. And if a boat is a fishing boat is there in the deep sea, they will never even realize that a tsunami wave has passed them. And the tsunami waves have a long, wavelengths, hundreds of kilometers, and their periods are a few minutes to about an hour. So the first wave can come, second wave can come within few minutes, as well as in an hour. So even if you see first wave, don't think that there won't be any other wave. Maybe after an hour, the next wave can come. And another property of these tsunami waves is that their speed, or the speed at which these waves travel, that is more or less proportional to the square root of the water depth. So in the deeper water, where the ocean depths are 7,000 or 4,000 meters, they can travel at 900 or 700, more than 700 kilometer per hour. So for Indian Ocean, if you consider in the deep regions, on an average, the water depth is about 4,000 meters. Or the tsunami which was generated in Sumatra, the water depths are about 4,000 meters. And in that region, the tsunami wave travels at 713 kilometers per hour. That means it is like a jet plane, or the plane what we travel. At that speed, the wave is traveling. That is why the tsunami waves reach the shore, the coast, within a few hours. It is like a jet plane take off from Indonesia and arrive at Chennai within a couple of hours. So that is the speed at which the tsunami wave travels. But as it comes closer and closer to the shore, when it comes on the shelf where the depths are lesser and lesser, or 100, 200 meters, it slows down because the friction of the ocean bottom, the ocean floor, it slows down. So it has to overcome that friction and travel. So it slows down. So it becomes 48 kilometer per hour or 159 kilometer per hour. Or for example, at a 10-meter water depth, it is about 36 kilometer per hour. That's like our car. So a tsunami wave which was traveling at jet speed, like a aeroplane, when it comes closer to the shore, it becomes like traveling in a car like. Of course, if a car hits you also, you are not going to be spared just like that. But when the speed is decreasing, its wavelength also gets compressed. The wavelengths which are nearly 300 kilometers in the deeper ocean, it gets compressed because of the friction offered by the ocean bottom. The friction increases as the depth decreases, and this entire energy is getting compressed and compressed and compressed within shorter wavelength. So the energy involved with the tsunami wave is much larger, because almost same energy, except the energy which is lost due to the friction, is preserved. And though it is at a car speed, its energy, the momentum at which it is going to hit the coast is much higher. That is why when the tsunami wave hits, everything what is there gets destroyed and gets washed off. So its height increases, its wavelength decreases, but energy flux gets preserved. So it is hitting at a very high energy, at a very high wave height. So what are the causes of tsunami? So to cause a tsunami, the ocean water column has to be disturbed. This one can disturb by an earthquake. If an earthquake occurs on the ocean floor, the entire water column will get disturbed. It will disturb the water column up and down. It will generate the waves. Or if there is an underwater volcanic eruption or an underwater landslide, if there is a huge landslide in the ocean, it is like you throw a stone in the pond, or you just create a mudslide in the pond. Any disturbance of the water column will generate the waves, because that energy is released and it will generate the waves, and the waves will start propagating. Also, if somebody can detonate a powerful nuclear device, like the recently those WhatsApp messages which are doing around, the North Korea is planning to destroy US by generating a tsunami. Theoretically, it is possible. I don't say no. If you can explode a very powerful nuclear device in the ocean, that energy will generate the waves, and those waves will travel exactly like a tsunami wave, with the same properties of tsunami wave, and can destroy the coast where which they arrive. And the fourth cause is if a large meteor, it hits the ocean bottom. It is like you throw a large stone in the pond, it will generate the waves. So these are the four major causes which can generate major tsunamis. But 99% of the tsunamis which have been recorded and which have been experienced, and the history has the memory, almost 98 to 99% of the tsunamis have been generated by the earthquakes. So most of the tsunamis get generated because of the earthquakes which are happening on the ocean floor. So if a major earthquake happens on the ocean floor, we can expect that it will generate a tsunami. But the question is whether every earthquake will generate a tsunami. That is where the warning center role comes in picture. So if you just to give you an idea of kind of the losses during due to the 10 most powerful tsunamis, or 10 most important worst tsunamis in the history. Of course, the number one rank is for the Sumatra, Indonesia tsunami on 26th December 2004. Its magnitude was 9.3, the earthquake magnitude. It was such a very powerful earthquake, the most powerful in the recorded history. And the loss, the economic loss which has been estimated is about 10 billion US dollars, and that killed 230,000 people, and several thousands still missing or unaccounted for. So that was most devastating tsunami in our recorded history. Then during our lifetime itself in 2011, precisely on 11th March 2011, Tohoku tsunami on the coast of Japan occurred with a magnitude of 9, and the loss, economic loss, is much higher because it mainly hit the one of the most developed country, Japan. So when you are most developed, your loss also is higher. If I am poor, I have nothing much to lose except my hut. But if I am very wealthy, I have a mansion to lose. So the economic loss is much higher. 235 billion US dollars were lost, and it killed about 18,000 people, because Japan is much more prepared than any other country, and that tsunami mostly affected the Japan. The third in the rank is the Lisbon tsunami on 1st November 1755, 8.5 magnitude, that killed about 60,000 people. And the fourth one is not a tsunami which is created by the earthquake. That tsunami occurred because the Krakatoa volcano in Indonesia, that erupted, and large quantity of lava was pushed into the sea. When this Krakatoa explosion occurred, a portion of that volcano, it just broke and slipped in the sea. Even recently also it happened, and though it was not a very major tsunami, it created a tsunami in the Java Sea just last year in 2019, 18 or 19 it was. So this was a major explosion, and it pushed a portion of the Krakatoa volcano into the sea, and that generated a major tsunami which killed about 40,000 people. Then Tsunada Sea, Japan, that is the fifth largest tsunami in 1498. Magnitude was 8.3, killed 31,000 people, and so on. You can see the most devastating 10 tsunamis. And if you see this list, out of 10, 6 occurred in Japan. So Japan is the most vulnerable country for tsunamis. There is a reason for that, because the Japan is sitting on the area which is most prone for the earthquakes. So, and it happens. And I have also listed the major tsunamis that occurred in our Indian Ocean. Of course, Sumatra tsunami on 26th December is the most powerful one which occurred. Before that, there was one after that when Bengkulu tsunami 8.4 magnitude on 12th September 2007. Of course, it was not very devastating tsunami. Then there was another one in 2006 in Java earthquake, 7.8, 17th July. And before our Sumatra tsunami, only we remember about the Makran tsunami. Makran coast is the coast which is near to Pakistan, Iran, that area. That is called the Makran area or Makran coast. And there was a tsunami, an earthquake of 8.5 magnitude, and a tsunami. Even today also, scientists are of two opinion what generated that tsunami. Whether the earthquake generated that 8.5 magnitude earthquake generated, or it is not the earthquake, but the landslide or the mudslide that followed the earthquake generated the tsunami. Still, there is a big debate is going on, and this question is not yet settled. Whatever it is, there was an earthquake of 8.5 magnitude, and there are evidences to also show that there was a large mudslide in that region, and that generated that tsunami. And we have the records of that tsunami all along our Indian coast also. And some of the records says that that tsunami reached up to Karwar in Karnataka, and it reached Mumbai and Karwar. But we do not have much information on the losses what was caused by that tsunami. But there are reports on devastating losses in Karachi, as well as Ormara and those regions in Pakistan, and also in some of those Gulf countries. But these are very sketchy records are available. Otherwise, we don't know much about that 1945 tsunami. Another tsunami which has been recorded by paleo tsunami scientists, as well as in the records, is this Car Nicobar earthquake, which occurred on 31st December 1881 with a magnitude of 7.9. And that tsunami, the evidences are available that that tsunami arrived even on the Andhra Pradesh and Tamil Nadu coast. We have very good evidences on the arrival of tsunami waves from this Car Nicobar tsunami on the mainland Indian coast also. So what causes this earthquake? Because 99% of the tsunamis are occurring because of the earthquakes. We should look at the reasons for the earthquakes. If you take a slice, like you cut the watermelon, so you just cut a slice of earth. Let us say that earth is more than 6,000 kilometer radius, and I take a knife and cut a slice of the earth and take out that piece. Then I will see that there are four distinct layers. There is a solid inner core at for few from 6,378, that's Earth's radius, to about 5,000 kilometers deep. That means about 1,000 kilometer thick solid inner core of the Earth. Then there is a liquid outer core. It's completely in a molten state, from 5,000 to about 3,000 kilometers. So about 2,000 kilometer thick liquid core. And then there is a semi solid type of mantle, what is called, which is again to about 3,000 to close to 100 kilometers. And above that is the solid part, which we are seeing as the land, ocean floor, mountains, etc. And that layer, which is not more than 80 to 100 kilometers thick, that is the skin of the earth where we live. And the issue is that the skin of the earth, that is not a complete solid or a complete sheet which is enveloping the earth. Though the earth is a sphere, the outer skin of this sphere, like a football, you have a rubber bladder inside which is intact, but the outside of the football is made of several pieces which are stitched together. Similarly, the Earth's outer skin is several pieces. You can see in the bottom picture, there are those lines drawn. There are two types of lines drawn. One line with staggered lines, and other one is with inverted cones on them. So there are two types of boundaries for these pieces, and each piece is called the plate. Or simply I can say that The outer skin of the earth is made of several pieces called plates. There are 7 major plates. Of course, within these plates, there are again the cracks. So it is a cracked plate. That is what we have. And why this is cracking? Because still the earth is consolidating. It is becoming cooler and cooler from its formation about for more than 4.5 billion years ago. So this from the inside, from the outer core and mantle, the molten stuff comes up, and it comes up and up, and it comes out through these cracks. So that is happening because if you see the ocean floor, it is not flat. It has mountain chains. See, if we say that the greatest mountains are Himalayas, that is what we study in our schools. The highest mountains are Himalayas, agreed. And their length is what? Only few thousand kilometers. But if you look at the mountain chains on the ocean floor, they are tens of thousand kilometers. You see in the Atlantic, from the north, somewhere near Greenland, that mountain chain extends, almost close to the Antarctic. So tens of thousand kilometers long mountain chains. Even in Indian Ocean, you can see that mountain chain starts somewhere near the Horn of Africa and extends one branch. After some time, it branches. One branch goes towards west, and the other branch goes towards the east. Again, 10,000s of kilometers. These mountain regions are called the mid-oceanic ridges. Even in Pacific, you can see on the eastern side of the Pacific, these mountain chains are growing. How these mountain chains are forming is because this molten stuff, as you see in that animation, that comes out, and these mountain chains where these ridges are there, the floor is getting expanded, or as the more and more matter comes out from inside the earth, these ridges are pushing this plate, so that from there it gets pushed because it cannot contain everything there. It gets pushed, and on the other side, as I have shown the other animation on the right side, the when it pushed, what happens? One plate goes and pushes the other plate, and one of the plate starts going below the other one. So these areas are called the subduction zones, and these subduction zones are the plate boundaries where where one plate is getting pressed against the other, and constantly it is getting pressed. If you look at the subduction zone in the Indian Ocean, right from Myanmar region all along our Andaman Nicobar Islands, extending to the Indonesian region, Sumatra, Java, and all those Indonesian islands. This plate boundary, or the Andaman Nicobar Indonesian subduction zone, that extends thousands of kilometers. That means the Indo-Australian plate, which is being pushed by the mid-Indian Ocean ridge, is moving towards pushing the plate on the eastern side, the Eurasian or Sunda plate, and it is pushing and pushing at different velocities. You can see that in the Burma or the northern Andaman region, about 59 millimeter per year, and in the south, in the Indonesian region, its speed is about 68 millimeter per year, And so with these different speeds, these plates are being pushed against each other. So when you keep on pushing this plate, and it is subducting. That means the Indo-Australian plate is getting going below the Eurasian or Sunda plate, keep on going down and down. Then of course it gets melted and goes into the mantle and outer core of the earth gets melted there. So this is a convective process which is keep on happening, and as this plate moves one below the other or against the other, some part of the plate gets stuck. It doesn't move much. So that part of the plate get stuck, and the rest of the plate is again keep on moving. It is like we are all running, and some part of the people could not run because of the this. Then there is a stampede, like. So that kind of a situation arises, and that plate which gets stuck, it can not hold for a long time. It breaks. When it breaks, it releases the energy. So that causes the earthquake, and that breaking can happen at 100 kilometers below or 10 kilometers below the ocean floor. Anywhere that breaking can happen. And when it breaks, as I have shown these three figures, you can see that the breaking need not be same every time. It can break in different ways. See, one is called normal fault. That means when it breaks, one plate just slips down. If it slips down, it is what we call in technical terms a normal fault, or just it slipped. It is gently slipped like. And the second type is called strike slip. So when it pushes and it breaks, it can just rub against each other because the energy has to be released. So it broke, and when it breaks, it can just slip against one another. That means it just slips parallelly. Not there is no vertical movement. And the third type is when it breaks, the broken plate just bounces, throwing the entire water column up. So that disturbs the water column the maximum. So the most dangerous from the point of view of a tsunami, most dangerous type of earthquake is thrust fault or a reverse fault earthquake, where when the earthquake occurs, it throws up the water. So if that is what is happening, like in 2004, that was a thrust fault earthquake, and that will disturb this water column from the tsunami point of view. That is the most dangerous type of the earthquake. Of course, normal fault also can generate a tsunami, but it will disturb the water column to a lesser extent, and that tsunami need not be, I don't say it will not be, it need not be a devastating tsunami. So the issue is, if we have to warn, first we have to detect where the earthquake has occurred, and what type of earthquake that has occurred, to be precise. If we detect only the earthquake and estimate its magnitude, then some of the job is done. We know where the earthquake has occurred. Whether the earthquake has occurred on the ocean floor, then we have to be careful about a tsunami. And if it is of higher magnitude, we have to be careful that can generate a tsunami. But even every higher magnitude earthquake need not create a tsunami. For example, if the earthquake has occurred because of the strike slip fault, then it need not create a tsunami. And that is what happened in 2012. We had a large earthquake, 8.5 magnitude. I will come to that little later. And no tsunami was generated. Very minor tsunami was, a small minor tsunami was generated. And but the earthquake magnitude was large, though not like 2004 earthquake. This earthquake magnitude also was 8.5, which is good enough to generate a large tsunami. But luckily, that earthquake occurred because of a strike slip fault and didn't generate a devastating tsunami at that time. So when the earthquake occurs, the energy is released, and because of the energy is released, it generates waves. These are not tsunami waves; these are shock waves on the earth. So on the solid earth is broken at some place, and that breaking generates shock waves and shear waves. So these shock waves are called primary waves, and these waves can travel very, very fast. Within few seconds, they can travel all around the globe, and they will travel all around the globe within few seconds and less than a minute. And the secondary waves or shear waves, both these are body waves, or they are occurring on the body of the earth, and they will travel at much faster speed. So even before the tsunami, if tsunami is traveling at a jet speed, these waves are traveling at a much higher, 10 times the higher speed of a rocket, not even a jet. So these waves will arrive at distant locations much faster before the tsunami. So that is good for us. So that means we can detect the earthquake where it has occurred much before the tsunami waves come to our region. So what we can this most importantly, there are four types of waves. One is called a primary wave. It's a pressure wave, so it is a back and forth motion. And secondary wave, shear wave, that is another type of wave. And then there are surface waves called Rayleigh waves and Love waves. They also will travel. And when these waves pass through the earth, it will shake whatever those locations and whatever on the earth. That's why when an earthquake occurs, our houses, the buildings, everything gets shaken, and even they can collapse if they cannot withstand that kind of a shaking when these waves pass through. That is what it happens. So if we keep some instrument called, if I have a very heavy pendulum which is hang at a location, very heavy one, and a drum on which I can put a chart, and this drum is rotating at a clock speed, and this along with this drum, this chart also is moving. And if I attach a pen to this pendulum, it will whenever this waves comes, this base of this instrument, it will also move back and forth, and this pen which is just hanging at a from the pendulum, which is at which is sturdy, will draw those waves. You can see the kind of waves. This is a simple instrument which is called a seismograph or a seismometer, because earlier days it used only a pendulum and a chart, and it draw this graph on that chart. So it is called a seismograph. And these days, of course, we have the modern electronic instruments to detect these waves and record them. So these days we call them seismometers, or whatever it is. These waves, primary and secondary waves, they are shock waves. They travel all around the globe, and if we have a seismometer, we can record these waves. So but there are properties for these waves. The P waves, which travel much faster than the S waves. Of course, both are traveling at a much higher speed than any other wave. That's why the both of them arrive all over the can travel all over the globe within less than a minute or maximum 2 minutes. but the P waves are comparatively faster than the S waves. So if an earthquake occurs somewhere, let's say in the Sumatra region, and if I have a seismograph in Hyderabad, first I will record the P waves because they arrive fast. Then comes the S waves. And if I can distinguish this P and S wave and the time difference in their arrival, I can estimate what is the distance at which this earthquake has occurred. So I can find out from Hyderabad at what distance this earthquake has occurred. So I know I have the P waves arrived on my seismograph. You can see how the P wave looks like and how the S wave looks like. And the experienced geophysicist, they can identify these waves, P wave and S wave from these seismographs and mark and you can take the time difference between the P and the S wave arrival, the first arrival of the P wave and first arrival of the S wave. And from this time difference, you can, and you know the velocity of these waves, so you can find out from which distance or what is the distance from which they are coming. But the issue is that when I calculate this distance, it can be north of Hyderabad, south of Hyderabad, west of Hyderabad, or east of Hyderabad. So I don't know whether it has come from the Sumatra, or it has come from Makran coast, or it has come from. Only thing I know is that they came from about 4,000 kilometers or 3,000 kilometers away from Hyderabad. That's all I know now. So how to find out that? Then only I can fix the location. If I say that this an earthquake has occurred about 3,000 kilometers away from Hyderabad, of no use, because it can be the earthquake can be in Himalayas, earthquake can be in Pakistan, earthquake can be in Indonesia, earthquake can be somewhere else. We don't know. So what I do is I take that data, and for the Hyderabad with a center as Hyderabad, draw a circle. So the earthquake, as far as I am concerned, who is sitting in Hyderabad, the location can fall anywhere on that circle. So I will draw a circle. Then my colleague is sitting in Delhi. He also has recorded, and he will also do the same. He will draw a circle. Then I have a colleague, for example, who is sitting in Colombo. He also is recording and doing the same thing. So individually, three of us, we know only that the earthquake has occurred on the circles which we have drawn, with the center as Colombo, center as Hyderabad, or center as Delhi. And unless we three of us talk together and exchange our circles, we cannot find out exactly what is the location. So if we three of us join, we put these three circles on the same map. Then these three circles, because of the difference in distance to that earthquake location from each of us, the distance from Hyderabad is different from distance from Delhi to Sumatra, or from Colombo to Sumatra. So when you put these three circles, those three circles will intersect at one location, maybe at two locations. But most likely they will intersect at one location only. So that the intersection is the actual epicenter of the earth. So I know now to find out from what distance the earthquake has occurred, and also I know where the earthquake has occurred. So this is the job I have to do first, to find out where the earthquake has occurred, and from these records of the P and S waves, and depending on the magnitude of the earthquake, those wiggles which I had shown you earlier, they will be larger or smaller, and based on that, there are techniques to calculate the magnitude of the earthquakes. So based on that, I can calculate the magnitude of the earthquake also. And if I am more expertise, I can also find out what type of earthquake has caused, depending on the properties of these waves. I don't want to go in details right now, but based on these properties of these waves and using certain mathematical functions and algorithms, I can immediately find out what type of earthquake has occurred in that region, whether it is a normal fault, whether it is a strike slip, or whether it is a reverse fault earthquake that has occurred in that region. So normally this magnitude of the earthquake is represented in Richter scale. Charles Francis Richter, working in Southern California, he was working in Scripps Institution of Oceanography, one of the famous institution world over, located in San Diego. He was a geophysicist working there. He defined a method to define the earthquake magnitude. But he defined that based on certain conditions in South California, earthquakes which are occurring, and also based on the kind of instrument which he developed, and that is what he used. And he used some logarithmic functions to quantify the energy released. So when we say 8.5 or 9, it represents a number which is proportional to the energy released by the earthquake. Of course, in 1970s, that Richter scale was modified using a more generalized definition called moment magnitude scale. And these days, we all use this moment magnitude scale, though everybody reports as Richter scale. Actually, we are reporting is not at the Richter scale. Even in a tsunami or earthquake reports, you will see that the magnitude of so and so occurred of Richter scale. Actually, not. It is a moment magnitude which is used and reported. Because it is on the logarithmic scale, one magnitude of increase, for example, 8 to 9 increase. If a magnitude was 8 and the magnitude is 8 and 9, then the energy released is tenfold. So from 8 to 9, if earthquake magnitude is 9, means it has released 10 times the energy than the earthquake which occurred at magnitude of 8, and the corresponding the tenfold increase in the amplitude of the earthquake, and 31.6 times the increase in the energy release. So if you compare two earthquakes of 8 and 9, the energy release is more than 31.6 times, or for each 0.2 increase in the magnitude, for example 8.2 or 8.4, the energy release is double. So if you want to assess the actual impact, you should have the clear or the very precise magnitude, and your errors in this estimation of the magnitude should not be more than 0.2, because if 0.2 you make an error, that means you are going to double the energy release and make mistakes in estimating what kind of devastations that particular earthquake can create. So these days, I need not call my friend in Delhi or Colombo, because everything is in digital. So there are hundreds of, actually thousands, not even 100, thousands of seismometers are installed by almost every country to record these earthquakes. And a few hundreds of them, for example, the Tsunami Early Warning Center in Hyderabad at our institute, we receive data from about 400 or 425 of them. You can see that map with little triangles, which shows the location of seismometers from which we are receiving the data. It is not that we cannot receive from others, but every country do not share all the data. For example, in India, we have hundreds, I think nearly 130 seismic seismometers, but we share with the others from only 4 stations. So of course, that data, all the data is available to us because we are government agency in India. Similarly, in US, they may have thousands of them, but they share only a few hundred. And other countries also very share a few, but that is good enough to detect the large earthquakes. So if you have more of them and more data is coming from more seismometers, your accuracy is in determining the location as well as the depth of the earthquake and the other properties of the earthquake like magnitude and how long the rupture has occurred. All these increases. So if you have fewer stations, your accuracies are low, and if you have more, you can have more accuracies. So this is the kind of data that comes to the early warning center. Keep on transmitting this data, and we can receive this data. Even if there is no earthquake also, there are these waves, P and S waves keep on arriving, but of lesser magnitude, and they will keep on coming to our computers like this within a few seconds. You can see that red line and the each of the wave which it is just a few minutes. Within few minutes this data keeps arriving, and the computers are constantly analyzing this data to find out whether an earthquake has occurred at that particular time, and it will calculate its magnitude and warn the early warning center automatically. We have automated the entire process of receiving data from 425 seismometers all over the world, and plus more than 100 seismometers from Indian region, and keep on observing this, analyzing this. Computer does for us. So computer keeps on analyzing these records and try and determines the location and magnitude of the earthquake. For example, the earthquake which occurred on 11th April 2012 west of Sumatra Island in Indonesia, its magnitude was 8.5, and you can see those that red circle, that's the location of the earthquake west of Sumatra, and you can also see those lines from which the data was used. So those lines represent the seismic stations which reported data, and the computer judiciously used the data to determine that the magnitude of, so hundreds of seismometer data was used to determine the magnitude of that particular earthquake. So once we determine that magnitude of the earthquake, then to issue a tsunami warning, the next step is find out for that particular earthquake how much water column got displaced. So for that we use a mathematical numerical model, what is called tsunami model, and using that model, for example, if the seafloor has displaced by 1 meter, so how much that shock or that energy could displace the water level at or the seawater, the water column. So that we can do with some mathematical formulations, most popularly known as Okada solution, and convert that as the displacement. And once that displacement is determined, then we can use the numerical model to propagate that wave from that location to different directions. So that is what, so you can see that the wave has been generated, and one crest of the wave is going towards the west, and the trough had gone towards the east to Thailand and those regions. And if you read the report in 2004 tsunami, you know that Thailand, first the sea got completely exposed, and people all who are on the beach, they run into the sea because of the curiosity, and they all got washed off. The mainly the tourists in Bangkok and Thailand that those coasts. So you can generate this using a numerical model, and that is what we do as the second step once we determine where the earthquake has occurred and what are its magnitude. And using this model, then I can calculate what is the arrival time along my coast at different locations. Each location I can determine what is the expected arrival of the tsunami wave and what is the expected height of the tsunami wave. So I have divided the entire coast in few tens of kilometers, 50 to 70 kilometers to cover each district. So now I know in each district, Nagapattinam district, what is the arrival of tsunami wave and what is the height of that tsunami wave. Similarly, for Krishna district, I know what is the arrival of tsunami wave, and or I can guess what would be the height of the tsunami wave which will be arriving at that location. So this gives one advantage. So if I take the magnitude of the earthquake and say that even for a 2004 tsunami, its magnitude was 9.3, highest magnitude. And if I say that the entire coast is going to get affected by tsunami, that need not be true. And we have seen that most of the devastation was in Nagapattinam, some parts of Chennai and Kerala coast, and of course Andaman Nicobar Islands, but not Puri and those coasts or Gujarat coast and those. So we have to find out which are the locations on the coast which are going to get the very high tsunami waves, and that is possible because of this mathematical numerical model. And I'm happy that we are the ones to introduce this concept in the tsunami early warning chain, that use of the numerical model once we know the earthquake parameters and run that model and see the expected time of arrival of the tsunami wave and the expected height of the tsunami wave at a different location, and make use of that to issue the warnings. So what we do is if the tsunami height is more than 2 meters at certain stretches of the coast, and that arrival time is less than 60 meters, that is less than an hour, we don't have much time. So we issue a warning for that particular stretch of the coast. And if even if it shows more than 2 meters, and I can wait some more time, the arrival time is more than 1 hour, that means I have some more time on my hand, I will not ask I will not issue a warning for that stretch, I will issue only a alert. So I will issue based on that warning, alert, watch, like these three categories of warnings to the disaster managers. So wherever we issue the warning, that means the disaster managers should immediately evacuate the population on the coast. People who are living on the coast should go to the higher grounds. They should evacuate there. And if the regions where the alert is issued, they need not evacuate, but everybody be prepared and be ready for the next step. And those who are put under watch, they be aware of there could be a tsunami, but there is no need of any panic. There is nothing, no action has to be taken. And by this time, after a few minutes, the tsunami wave, if it has generated, it has traveled, and it can get recorded at different instruments which are kept at sea. I will come to that. And based on that, if I see that there is a significant tsunami has been generated, because if I measure the sea level using a sea level gauge or a tsunami buoy in the middle of the ocean, then I am certain that my numerical model is more dependable. Then, if still the numerical model is showing greater than 2 meter wave height for that particular location, I will convert that as warning and issue the warnings to the disaster management authorities that you please evacuate the people from these regions as well. So that is the so first so that using this numerical model, I can issue a threat map which shows the warning. This is a threat map which was issued for the 2012 earthquake at 8.5 magnitude. It was a large earthquake, and the warning was issued only for the 3 islands in the Andaman Nicobar group of islands, and even rest of the Andaman islands only alert was issued, and for the entire east coast of India from West Bengal to Tamil Nadu and part of Kerala coast, only the alert was issued because the numerical model showed the wave heights less than 2 meters, and the rest of the west coast only the tsunami watch was issued. So by issuing this kind of graded warnings, the advantage is that the government machinery need not get stressed, people need not get panicked, and everybody need not run for their life where a tsunami wave is not going to arrive. And we turned out to be the right. No tsunami wave arrived on our coast due to that tsunami, because that tsunami, that earthquake was a strike slip earthquake, and very minor tsunami was generated. Even for Andaman Islands, it was not a devastating tsunami. This so this technique allows us to give more of location specific warnings than a general ocean basin wide warning. So to detect the tsunami waves, there are different instruments are kept. Some of them you see that those dots, those green dots and those circles, they are in the middle of the ocean, and these are all strategically placed to detect the tsunami wave. For example, these seven dots, circles you see, they are the tsunami buoys which are deployed and maintained by India by INCOIS as well as National Institute of Ocean Technology in Chennai. We both belong to the same ministry, so we jointly do this job, and we deploy these seven tsunami buoys, five in the Bay of Bengal region and two in the Northern Arabian Sea region. We maintain that, and they have been placed in such a way that if an earthquake occurs in less than half an hour, we should be able to detect the tsunami wave which is propagating towards our coast, so that we can issue the proper warnings. And for example, this is an example of a tsunami buoy. It is nothing but a bottom pressure recorder which is sitting on the sea floor at a depth of about 4,000 meters or 4 kilometers, and it just sends the pressure change in the water column. So if a tsunami wave occurs and passes through that water column, this pressure will change, and it can detect even up to the millimeter level change in the sea level, and it will transmit that data to a surface buoy which is anchored nearby through acoustic telemetry, because radio waves cannot be used in the water. So using sound waves, that data is information is transmitted to the surface buoy which is floating on the sea surface, and that buoy in turn transmits using radio waves to satellites, and those satellites transmit that data to the early warning centers. So within a few seconds, the data from the BPR is transmitted to the early warning center. So when the tsunami wave passes over this BPR or bottom pressure recorder, we know that a tsunami has been generated, and we had to upgrade or degrade our warning process. In addition to that, there are several sea level gauges which have been installed and maintained by individual countries. In India also, we again INCOIS is maintaining 36 sea level gauges all along our coast, mainland coast, as well as in our islands of Lakshadweep and Andaman Nicobar Island. Similarly, there are sea level gauges which are maintained by Indonesia, Australia, US, several countries. So if a earthquake occurs near Indonesia, within minutes the tsunami wave will reach one of those gauges in the Indonesia, and we under the coordination of UNESCO, we all share this data with each other for the warning purposes. So India also we share from 8 of them out of these 36 with other countries. Similarly, we also receive data from Indonesia, Thailand, Myanmar, Bangladesh, and several other countries. So all these dot shows the sea level gauges what we receive from different countries. So these gauges also helps us in. They are also again very simple floats which are deployed in some sort of a well, and as the sea level goes up and down, that float will move up and down and report how much the sea level has changed. Or even today, the modern type of radar gauges using the microwaves just ping the water level and measure the changes in the water level. So the tsunami buoys as well as the sea level gauges helps us in detecting the tsunami waves if they have been generated, because every earthquake need not produce a tsunami. I'm just repeating that again. And when we use the mathematical model also, the numerical model also, it is not 100% accurate, because every model has its own inaccuracies, and we need not be 100% accurate. But these observations, they are the ultimate test. And when we receive these kind of observations, we can confirm and be calibrate our model and tell the disaster management authorities, yes, there is going to be a tsunami. And we have also now the technology to extend these models further on the land, because these models are now we use very finite element models, which we can even extend on the land and determine what could be the flooding in that region. In fact, we developed this model to predict the storm surge, because the storm surge runs up the water on the shore, and same model we converted adopted for tsunami also now, and it can run on a parallel computer, so it can run within a few minutes, and we have adopted this also. Now, not only that, we can tell the disaster managers what would be the tsunami wave height. We can also tell which are the regions which are going to get inundated, and to what level. I can even tell for some of the regions where we have done GIS mapping, whether your house will get inundated or not. Even that information is available for 9 locations: Machilipatnam, Tuticorin, Puri, and like that. There are 9 locations we have done detailed GIS mapping, and we know what kind of buildings are there in those regions, and we can even give that kind of information. So we have come up a long way from 2004, and we are able to provide this information. But we have to prepare the community to receive this information and act accordingly, because Just giving the early warning will not be sufficient. Our disaster management officials, they are taluka level or district level, they keep on changing. So what we do is we call them every year to our institute and conduct a workshop for them, explain them what does it mean, the warning, what does it mean the watch, what does it mean the alert, and how they should react, what they should do, etc., etc. And we also keep on testing because tomorrow somebody should not tell that oh, I didn't get the message, so I don't know. So every 6 months we call we do the test and ask them, did you receive my message, a test message, so that we know that the connectivity between the early warning center in Hyderabad and in Andaman Nicobar disaster management commissioner is intact. Whenever I call, he can get that information, or whenever we send the information, we are assured that he will get. So every 6 months, not only with the disaster managers in India, we also do the testing with the 25 other countries on the Indian Ocean rim, because we have to provide tsunami early warnings to those countries as well. And also we had to conduct the mock drills, because the coastal population or the local janata should know how to react or what they should do when the tsunami warnings are issued, and the DMOs the disaster management officers should explain. So for that, several mock exercises, at least once in 2 years, we conduct the mock exercise all over the Indian Ocean region, just to make the people aware and to be prepared for this tsunami. Some of the villages, they are ready for the tsunami, or they know exactly. I am very happy that two of our villages, one is Boxipalli in Ganjam, and another village in Jagatsinghpur district of Odisha. They are perfect. They know what is a tsunami and what they should do, and they even know how to recognize if there is a tsunami is going to come. Like if a earthquake is occurring very near to you and you are violently shaken, then don't stay near the coast. You be away. You go away from that coast. And if you see that the sea has withdrawn, don't rush to that sea. You will you are that is part of the tsunami wave. Trough has come first, and the tsunami wave crust is going to come. So if you see that sea has withdrawn, don't go to the shore. You run away from there, go to the higher land, because the tsunami is going to come. That's a clear sign of a tsunami. And also there are reports that even during the 2004 tsunami, there are reports that in Andaman Nicobar forests, the elephants, they ran to the higher grounds or the mountains from the coast. So maybe they can listen to these infra waves which human beings cannot listen. Our ears are not sensitive, but they can recognize and run away from the coast. So if they are running in large herds of animals are running, you also please run. Don't think much. Follow the animals in such a situation. Also, if you hear loud roar of water which is coming, that means the tsunami wave is coming. Don't wait there to watch that. That will be your last watch if you wait there. So run away from there, and time to time we should assess these risks involved and make the people aware of that, so that we can be safe from the tsunamis. So the conclusion of my talk is that there are we know what causes the tsunami, mostly the earthquakes, sudden lift of or drop of seafloor, and the disturbance of the water column. that causes the tsunami. And there are four major steps are involved in predicting the tsunami due to underwater earthquake. They are immediate detection of the earthquake within a few minutes. You should detect the earthquake because the time available is very short, couple of hours only. So normally less than 10 minutes time, I should be able to detect the earthquake, estimates its magnitude, and estimate the deformation on the seafloor, and then find out what is the predict the arrival time and the height of the tsunami wave at different locations on the coast, and then observe the tsunami waves using the tsunami buoys or tsunami meters and the sea level gauges, and fine tune the early warnings and immediately disseminate this information through a formidable communication channel. So these are all we have to do, but I have a caution. So though we are able to do detect the tsunamis and issue the warnings if they are causing because of the earthquakes, but we still don't know if the tsunami is generated by a landslide without an earthquake or following an earthquake, which maybe it strike slip, but it caused a landslide, and that landslide causes a tsunami. We have difficulty in giving the early warnings on that. For example, very recently in 2018, 28th September, in Palu in Indonesia, there was an earthquake of 7.4 magnitude, and based on the characteristic of that earthquake, no tsunami should have been generated, and that earthquake actually occurred on the land, on the island. But what happened was that that earthquake split the island in two, and one portion of the island was slipped. It was a strike slip earthquake actually, harmless earthquake from the tsunami point of view. But that strike slip pushed one portion of that island into the water. So when it was pushed as a landslide, it got pushed and it generated a tsunami. And no warning center could issue any warning for that tsunami. And unfortunately, about 1,400 people got killed in Indonesia nearby, because that tsunami was a very local tsunami, not a ocean-wide tsunami. But in that region, you can see that there are so many islands, and it's a closed region. In that region, 1,400 people got killed. So this is a challenge still we have to face, and we have to work out. So to know, if you have to create a early warning system, including this kind of happenings, we should know whether that region is susceptible for landslides. Then we can do something about that. And right now, we don't have information of entire area where the landslide can occur or which cannot occur. So with this, I conclude my talk, and thank you very much for your patience